I hope it works. We are talking about more subtle effect than the growth structure that we saw in the previous lesson, on the previous lecture. We now know that the spectrum of an atom is discrete, and we know how it behaves. So it goes like a 1 over n squared. N is a principal quantum number. We also know, thanks to treatment with the Schrödinger equation, that we have a quite a large degeneracy of levels, and this degeneracy of levels goes with the angular momentum. And that's more or less all what we know. But I remind you that all what we took into account until now is only a Coulomb interaction between an electron and the proton. That's all. This is, of course, far from being complete. So the story is much more interesting and complex. And starting from today, we are actually going to touch different subtle effects that are suitable to this system. And the first effect that we are going to talk about is the effect which is related to the spin of the electron. So we know, you know, and we know, everybody knows that the electron has spin. It's less evident what it is, right? So how it comes to the story. It's also possible, essentially, to show that there is no classical analogy to this sort of effect. The point is that the electron is a sort of an elementary particle, and this elementary particle has some features, right, that we relate to this. It has charge, it has mass, it has spin, and we know nothing about the size of its elementary particle, so it's essentially a point particle from our point of view. And we know that it cannot be divided. But we know that there is a certain spin, so if it's point particle, so spin cannot be associated with the rotation of the object, because the object is a point-like. So we consider it as a certain property of the electron, but this property has a certain effect which is actually related to a magnetic moment of the system. So I want to start actually to talk about this effect from describing some pivotal experiment in this history of modern physics, of course, but the physics in total. This experiment is called the Stern-Gerlach Experiment. And this experiment I'll try to describe in quite a detail. There is a reason, so it's not only describes. So it was not only the experiment that discovered the spin of the electron, but it's also an experiment that helps a lot to understand several crucial steps in the story. First crucial step will be today, so which is related to spin. The second crucial story will be related later in the course. We will meet it toward the end when we will introduce density matrix instead of a function. So we'll be back to this experiment again in order to describe to show how it goes into the story. So I want to start from actually describing the magnetic moment of the system, and in order to describe it, or in order to define it, we want to consider it actually classically. So we don't want to. So we are doing some sort of classical arguments in order to show that there is a magnetic moment in the story. And more interestingly, we are not starting from spin. So essentially, it's also interesting to understand that, you know, in 1930, the year Bohr wrote his model, nobody really knows about the spin of the electron. So this was not in the story at all. But people knew is that there is some quantization of energy levels that is coming out of the Bohr model. And also it was related to the angular momentum. So if there is an angular momentum, then we can actually associate the angular momentum to the magnetic moment. So what we are going to do now is we are going to associate angular momentum of the electron to the magnetic moment. So this is essentially quite simple classical argument, which goes like that. So we know that we need to find current. So we are considering a really classical orbit of the electron, which goes around the proton. So it goes around in circles, which creates a current, right? Electric current on the circuit. So this electric current is equal to the charge. So the charge is the electronic charge divided by time, and this time is essentially the time which takes the electron to complete a single orbit. So this can be written, this time can be written differently. So it's a charge of the electron multiplied by the velocity of the electron on the orbit divided by the length of the orbit. So length of the orbit is equal to 2 pi multiplied by the radius, right, of the orbit. So now this is the current. So we know that the magnetic moment associated with the current loop is equal to current multiplied by surface, which is encircled by the current, right? So we have the current that is calculated here. So this is just V divided by 2 PR. We know the surface of this circle. So there's a PR squared. So pi is gone. We have here some E multiplied by V divided by 2 multiplied by R, right? So EVR. So this is the magnetic moment. So of course, because this is the vector, so the vector here is the direction of the surface. So it should be multiplied by a unitary vector which is associated with the surface. This is not the operator. This is the unitary vector associated with the surface in order to keep it like a vector. So magnetic moment is a vector, so we have to keep it vector. So we have to keep direction and the value. Okay, so now we can relate. So this is the magnetic moment related to the current due to the electron that encircles the proton. But we know that there is a angular momentum of the electron, which is also related to the rotation of the electron around the proton. So these two values can be related to each other, right? And this is, of course, because there is a multiplication of the velocity and the radius, right? So this multiplication of the velocity and radius gives immediately the value of the angular momentum. So we can say that our story goes like E 1 over 2 1 over 2 multiplied by VR. So this gives us the momentum almost, right? What is missing here is the mass of the electron that has to be multiplied here and divided here. So now this gives us the momentum, linear momentum multiplied by R. So this is the value, right? But the direction is the direction of the surface. So it's also meets the direction, so it's a perpendicular, right, to the direction of the velocity and the radius. So then we can, so this means that the we have sinus theta equal to 1. So here this gives us just the value of angular momentum. And I forgot here to multiply by the charge of the electron. So now we have the complete story. E divided by 2m multiplied by direction, multiplied by the angular momentum with the direction, with the correct direction, right? So now we have the relation between the magnetic moment to the angular momentum of the story, multiplied by the charge of the electron divided by 2m. So this angular momentum is measured in units of h bar in the quantum mechanics, right? So the h bar has a unity of the angular momentum. So this means that we can actually get the following. So if we divide here by h bar and multiply here by h bar, we have here a certain value, which includes only constants of nature. So it's a charge of the electron, h bar, which is the constant of Planck, divided by the mass of the electron. So this value is known as a Bohr magneton, or elementary magnetic moment, which is related to the motion of the electron in the atom. Because this value is now actually unitless, right? So this magnetic moment is equal to some unit of the magnetic moment. So this is elementary magnetic moment multiplied by some integer value, because the L has is integer value. Okay, so this gives us yeah, it's a vector size, yes, of course. So it's a vector, but it's vector without units. Okay, it's a unitless vector. Okay, so now we have here the relation between the magnetic moment and the angular momentum. And this is actually starts a certain search. So generally, we can always write this type of the relation. I will write it just here outside. We will come back to this relation again and again and again. So it generally comes with a certain sign value. There is also gyromagnetic ratio, so we'll come back to this gyromagnetic ratio. So this is a constant multiplied by Bohr magneton multiplied by a angular momentum, which is generally is marked by J divided by H bar. So we will come back several times to this expression today. So this is some general conclusion. Now what we want to do is we are getting to this expression, and this expression gives us the idea that, so there is a certain minus should be in this story. Usually it's marked by minus because the mu b is essentially a value which is a positive constant. Mu b has a value. Its value is equal to, let me put on this number, 9.274 multiplied by 10 to the minus 24 joule per second. Sorry, joule per divided by Tesla. Sorry. Yeah, I'm just not still didn't come down to earth. Okay, so this is a certain number. So I don't remember this number. I remember a different number. I'll show you what number I remember, which is much easier to remember. The reason I don't remember this number is it's in strange units of joule divided by Tesla. There's nothing strange. It's just the energy divided by magnetic field. This is the units of the magnetic moment. There is some much easier expression to remember from the Bohr magneton. We will come to it a bit later. So now what's going on? So now we have this magnetic moment. So, and if there is a magnetic moment, we can insert this magnetic moment into the magnetic field, and the magnetic field will insert a certain torque on this magnetic moment. And this torque will try to align the magnetic moment with the magnetic field, right? So that's quite a simple understanding. So what we know from the classical physics is that the time dependence of the angular momentum should be equal to torque. Torque is applied, right, by some external force, and this external force will be produced by the magnetic field, and try to align. Try to change angular momentum with time, right? And this change of the angular momentum with time is equal to torque. So now, if we are going to write it down, as we now know that this relation, right, out of this story. So we have here m, magnetic moment, which is equal to minus mu b multiplied by L divided by h bar. Therefore, from this story, of course, the L is just equal to the inverse of this guy, minus h bar divided by mu b, right? So now this, we want to take the derivative with time and equalize to torque. So we know that the torque is equal to a cross product of the magnetic moment with the magnetic field. So torque is the magnetic moment cross product with the external magnetic field. This is just a general argument from classical physics. So, but we know now that the magnetic moment is related to the angular momentum. So we can write down these two equations together, substituting the value of the L from here, and we get that the magnetic moment, the derivative with time of the magnetic moment will be equal to mu b, the magneton Bohr divided by h bar multiplied by b cross product with magnetic moment. So that's the equation of motion of the magnetic moment when we insert this magnetic moment in the magnetic field. So this is well known, right? So from classical physics. So this equation is the equation for the gyroscope, right? This is what you also should know. This means that we are taking right, the angular, so the magnetic moment, so this is the magnetic field. Let's suppose that the magnetic field goes along a certain direction, it's uniform. So here we have the magnetic moment. So this equation of motion, try to align the magnetic moment with the magnetic field, that this alignment actually acts as a force to this magnetic moment in this direction, and this direction, or actually in that direction, that goes inside the the board, and this force rotate the magnetic moment around the magnetic field. So that's the precession, right? So this is a certain precession, and this precession occurs with a certain frequency. And this frequency is known as the Larmor frequency of the problem. So this Larmor frequency is described by the relation between the magneton Bohr, right, and the magnetic field. So we can say that the magneton Bohr mu b is equal to h bar omega L, Larmor frequency, divided by the magnetic field. So we can understand this relation just analyzing the unity of the magneton Bohr, right? So the magnetic moment. Now we are having this value, right? This value is the Larmor frequency. This Larmor frequency is equal to mu Bohr, magneton Bohr multiplied by magnetic field divided by h bar. So that's the Larmor frequency of the precession of the magnetic moment in the when it is inserted in the magnetic field. So that's essentially what we get out of this simple analysis. So what does this mean? This means that, you know, there is an electron in the story, right? This electron makes an orbital motion around the proton. So this orbital motion creates a magnetic moment, which is actually in the same direction, right? So this magnetic moment is in the same direction as the angular momentum. So now if we apply magnetic field, so now we take the atom and put this atom in the magnetic field, so we know that the electron will make, so not the electron, sorry, the magnetic moment of the electron will start to precess around the direction of the magnetic field. That's what this story tells us, and we know how it precesses. So the precession frequency, right, the rate to rotate around this magnetic field is equal to the Bohr magneton multiplied by the magnetic field that we apply divided by h bar. So that's the Larmor frequency of associated with this new force which is applied on the system, or new field also, the magnetic field. So this is all classical, right? So this is all classical. This is complete classical analogy. We will come back to quantum treatment of the magnetic field applied on the atom a bit later in the course. But now this is enough in order to understand what's going on in the experiment, which is Stern-Gerlach experiment. That's the idea that I want to describe to you. Right, so now what's the idea of the experiment? So Stern-Gerlach suggested a simple, based on this simple analysis, suggested a simple rule. They say, if the angular momentum quantized, then the magnetic moment is quantized. That just comes from the same argument. They are related to each other. And the magnetic moment of an atom, we know how to measure. So we can imagine how to measure. Magnetic moment is something that we know from the classical physics. Once the magnetic moment is inserted into the magnetic field, we can actually apply a force on that. And in addition, if the magnetic field is not uniform, right? So if we are not putting the uniform magnetic field, but the gradient or change of the magnetic field as a function of the space, then there will be a real force applied on the object, applied on the electron, and this force will somehow change the beam of atoms. So that's the idea. Let's write down how it works in simple equations, again based on classical physics. So we know that the force, the mechanical force that is applied should be equal to minus gradient of the potential, right? So, and the interaction potential between the magnetic moment and the magnetic field is just the multiplication between the magnetic moment, dot product between the magnetic moment and the magnetic field. That's the interaction energy, right, between the magnetic moment. Well, the interaction energy caused by the presence of the magnetic field, which is applied on the magnetic moment, right? This is probably the more correct description. Now, we know that if this happens, so there can be a force which will be applied on the system, and this force is essentially a divergence of this energy, right? So the divergence of this energy, so now I can say that F will be equal to divergence of the dot product of mu and B, right? So it's a divergence of the dot product between the magnetic moment and the magnetic field. Now, it's quite a complex expression, right? Because these are two vectors, but what we consider here is that the magnetic moment does not depend on space, so it's always the same. It's not depend on x, y, and z. So we took it out of the story, and what we need to do is just to apply. Then the divergence will be actually applied only on the magnetic field. So we can essentially write down the expressions for the force which is applied in each different direction. So I can write the whole expression, of course, but the whole expression will be sort of like a sum, right? So we can extract the mu out of the story, but then we will have to sum over x, y, and z, mi element multiply by the divergence of the magnetic field Bi. So if I write down this according to different elements that are playing a role in the story, I'll have 3 equations for different direction of force. So we have the fx, like let's go each element of the story. So fx is just equal to mx, this is what is written there, multiply by the derivative of bx according to all directions, right, that we have here. So according to dx plus db x dy plus dbx dz. So that's only fx, right? So if we write everything correctly, so fy would be my multiplied by the sum of dby according to directions dby dy plus dbz dz, and fz will be equal to mz multiplied by dbz dx plus dbz dy plus dbz dz. This is the whole story, right? So if it's written correctly, so this is how it should look like. So the force is applied according to all changes of the magnetic field in all possible directions. Now let's try to imagine the experiment. So we know that the force will be applied if we take care that the magnetic field changes as a function of distance. So the idea of Stern-Gerlach was to construct, so now I will describe the Stern-Gerlach experiment. So the experiment was done in 1922. This was a pivotal experiment, so in the history. It's so pivotal that people still use this technique. This experimental technique is continuously used in different parts of the world. It's extremely strong experimental tool. So this is the idea was to take the gradient of the magnetic field, create the gradient of the magnetic field with this type of magnet. So these are permanent magnets. We'll try to draw it nicely. So like that. Like that. So this is the piece of magnet, and I hope you can see that this is sort of a sharp piece of magnet, right? So it's a bulk, and it's made very sharp toward the sharp end here. And from this, from below down, here we have a plate. With a different direction of the magnetic field. So this is the plate, a regular one, which is just below. So this one is a south pole, if I remember correctly. Let me check that. Yes, so this is the south pole of the magnet. This is directed towards the north pole of the magnet. So we have here a certain, right, so we have here on the base a certain magnet which is quite large in size, right? And here we have a very sharp edge of the magnet. So you can imagine how the magnetic field looks like, right? So the magnetic field goes towards the edge, and it becomes very, very dense here. So the strength of the magnetic field here is very high. The strength of the magnetic field here is relatively low. So now we can draw this probably also with this simple representation, right? So like that. So and here we have the magnetic direction of the magnetic fields. So this magnetic field is weak here, becomes larger and even larger. So and then it's weak here, larger and larger, weak here, becomes larger and larger, right? So that's our magnetic field schematics drawn with the lines of the magnetic field. This is what we know. Now, what we do? We have here a beam of atoms. So this is we put here an oven. So there is an oven in the story. This oven has an opening toward this direction, and there is a beam that goes in this direction of atoms. So the atoms that are used in this experiment are silver atoms. So it's argentum. There are silver atoms. This is what they use. And now we can put the directions of this story. So this would be the Z direction. This would be Y direction. This would be the X direction. So X, Y, Z. These are our coordinates. So in this direction, right, this is the change of the magnetic field in Z direction. And the atoms are actually going through the gradient of the magnetic field. So let's suppose that we are actually going at the position which we will call as x and y equal to 0 position. So this x equal to y equal to 0. So that's the y here, that's the z at the x. So let's suppose that we have a symmetry of this apparatus, right? And we are taking this plane to be x, y, 0 plane. So and we also suppose that the atoms actually go very close to this symmetric plane of x, y equal to 0. Now, once atoms goes through that, to this gradient of the magnetic field, so what do we expect? So we expect that in this beam, this is a thermal beam of atoms, so the magnetic moment is actually distributed randomly between all possible directions. So we know, looking at this story, we can actually imagine that the main force that would be applied in this story is the change in the z direction, because the magnetic field mainly changes in z direction, right? So because we choose to walk very close to symmetry of the device. So this means that actually, according to symmetry of all this story, those two terms will be equal to 0, and mainly the force will be applied in z direction. So the force will be the momentum, the magnetic moment, projection of the magnetic moment on the z-axis multiplied by the change of the magnetic field in z direction. So that's the main force that is used here. Also, we can show that these two guys will be actually equal to 0 because of the previous picture of the oscillation, right? The precession of the magnetic moment around the direction of the magnetic field. Right, so if you can see that the precession gives me a projection on the x and y axis, which is rotated in the xy direction, right? So, and if I make the time averaging of the rotation frequency, so the rotation frequency is quite high. So the rotation frequency is the Larmor precession, which is equal to Bohr magneton. So it's quite large frequency. We'll give this exact value a bit later. So then this projection is actually rotated in xy direction. So if you make the averaging over time, this will give us 0. So in the direction of x and y, the force is actually equal to 0. So this 0, this part is 0 due to, to the symmetry of the apparatus. And the only force that is actually remains in this story is the force which acts in the z direction. So now we are having a beam of atoms that goes through the apparatus in the gradient of the magnetic field in z direction. So we have the distribution of the magnetic moment, which is random in all directions along the z-axis, right? So this is the only relevant axis of the story. So if they are randomly directed, what do we expect? So let's start from the situation. So now here, this is the detector. And this detector, this is just a detector. This detector knows to count atoms that come to this detector. So essentially, in the way that the first experiment was done is amazing, I would say. So this is not by chance they took the silver atoms. The silver atoms actually stick to a certain plate, and this plate, after you deposit silver for quite a long time, you can take this plate out of the vacuum system. That was, of course, in the vacuum. So you take this plate from the vacuum and you see right with your eyes where the silver is. So that's the experiment, right? So, believe me that depositing atoms one by one is not a very fast process, so you have to wait quite a long time. So you put the gradient, you wait, then you extract, you see, nothing happens, so you break your head, try to understand why. So then you think that you understand why, then you repeat the apparatus. So you repeat the experiment for another day or two, you extract, you see nothing, and so on and so forth, right? So this is not a simple type of the experiment. But let's suppose that our experiment is simple. So we detect each atom that arrives at this detector, so we can really see, we can count the atoms that arrives at this detector. This is also possible, but with a different type of atoms, so it's a more modern type of the experiment. But suppose that this is what happens. So now, let's take this magnetic construction out of the story. So what you see in the experiment. So what you see in the experiment is this type of signal. So this is the plate. And on the plate you will see some sort of distribution of points. Right? So this distribution of points will be sort of symmetric if we take this beam symmetric from the start, right? So that's what we will see in the experiment. If the magnetic, if this magnetic device is taken out of the story. So now, if now we take, this is no magnet, right? So this is the initial, if you wish, distribution. Now, if we take the magnetic field applied, so we take this magnetic gradient and put on the way of the beam, so what do you expect to see? So from the classical point of view, so we know what happens, right? So there is a force which is applied on magnetic moment, on the projection of the magnetic moment on the z-axis. So, and if we consider the classical gas, then we can imagine that the distribution, the initial distribution of all magnetic moments are actually uniform along the z-axis. So there will be a uniform spread in the z direction, right? So this is what you would expect. So the force will be sort of will take this sign and will make this sort of the elliptic shape, right? So we will expect to see something like that. That's according to this analysis and classical analysis and the fact that initial distribution is random along the z-axis. Well, the famous experimental result that was observed by Stern-Gerlach was neither that nor that. So, well, not that. Well, so the experimental result was like that. So this is what they observed, right? So they saw actually two distinguished spots on the screen. So that's the depositing screen. So we take it out and we see that there is two different spots that we observe. So this is nicely presented on the board. So you have to take into account that this experiment nearly failed. So one of the problems of the experiment was that that people really didn't understood well what is the structure of the atoms and the interaction of the atoms with the magnetic field. So anyway, the point is that these 2 points, these 2 spots were quite close to each other, so they barely were distinguished between them. But happily, they actually could be able to distinguish between these two spots, and they said, okay, now we actually understand that the result of this experiment shows some sort of a quantization of the angular momentum. So this quantization is because we see the quantization of the magnetic moment, therefore there is a quantization of the angular momentum. So everything is okay, of course, but there is a problem, right? So what is the problem? Problem is that there is only 2 spots here, right? So what does this mean? So this means that we cannot really relate angular momentum to two different values. Angular momentum is a whole number, is an integer number. So it's either 1, 2, 0, 1, 2, 3, and so on and so forth. So this means that the projection of this angular momentum, right? So the projection that can goes from the negative to positive. This is what we saw last week. So the projection should go, m of L should go from minus L plus 1 to to L, right? So, and if L is integer number, so we cannot get anything reasonable that will give us only two spots. So it cannot be 0. 0 will give us a 0 spot. It cannot be 1, because 1 will actually give us 3 different projections on the z-axis. So it will be minus 1, 0, and 1. So it's again not two spots. So this means that this result actually says that, okay, there is a quantization of something. So there is a quantization of the magnetic moment, but this quantization of the magnetic moment do not relate actually to the quantization of the angular momentum, but it should be related to a different effect. And it was quite clear start from the beginning that the only possibility to see the quantization of this angular momentum if you allow the angular momentum to be half integer, right? So it has to be 1/2 in order to get 2 spots minus 1/2 and half. So the general theory of angular momentum that was very fast after that developed. So people actually realized that the general theory of angular momentum do allow half numbers, half integers. So these half integers, the question is, you know what to do with integers. So integers gives you angular momentum. So what this half integers gives. So then you have to realize that this half integer should be related to some different property, and this different property should be the spin of the electron. So fortunately enough, another fortunate fortune in this experiment was to work with silver atoms. So silver atoms has a single electron on the external orbit. Therefore, the spin of the electron is actually 1/2. So then you can see only 2 spots. So it's only 1/2 plus 1/2 minus 1/2. So why it's fortunate? So if you take a different spin, for example, with 2 electrons, there is spin. The total spin will be equal to 1. Recall that in the experiment, these 2 spots were much closer to each other. So if you, for example, take a spin equal to 1, then you will have 3 spots, and these 3 spots will be indistinguishable, and the results will be actually equal to the result of classical theory. So you will be able to distinguish a quantization of a certain type of angular momentum. So there are several fortunate things, right? Like it happens in the experiment. So you try to do something in the experiment. You are lucky enough to have good things that happens in the experiment. So you discover that. So you actually do not understand what's going on. It takes some time to realize that this is related to the spin of the electron. But you do demonstrate several important things. And this important thing is actually the quantization of angular momentum. And this technique, since that continues to be used in the experiment in order to distinguish between different spin states, or between different spin states of the atomic system. So this is how it's done only, also in experiments nowadays. So you put the atoms into gradient of the magnetic field, and then you apply gradient for a certain time, and then you see what happens with different spin states of atoms. So you can distinguish different spin states with that. So let me continue to describe this Stern-Gerlach experiment now with the quantum mechanical technique. So we will try to apply, so it's quite instrumental, quite instructive actually, to go and to develop a quantum mechanical approach to describe this experiment based on the experimental facts. Okay, so I will try to show you, it's something that you should know first. But something that will help us also in the later stage when we would like to introduce also a density matrix. We will try to describe this experiment with the quantum mechanical terminology. Okay, so we want to describe actually, right, several facts that we know from the experiment. So the first fact that we know from the experiment, that the beam is split into two spots, and these two spots means that we have two eigenvalues along the direction, right? So we have a certain operator, and this operator gives us two eigenvalues. So this eigenvalue is mu b plus mu b minus mu b. There are two eigenvalues of the story. And now this is the eigenvalues of a certain operator that we can call a mu z operator in the language of quantum mechanics. Now, we know that this actually plus mu b should be an eigenvalue of the eigenvector, and this eigenvector we can mark as plus along the z direction. This eigenvector is equal to 1, 0, and the eigenvector in the minus direction along z axis will be equal to 0, 1. So we know that these two eigenvectors are actually eigenvectors of the operator mz with the eigenvalues of plus mu b and eigenvalues of minus mu b. That's how we can describe the experimental fact of measuring two spots out of the experimental apparatus, right? So now we can say that, you know, so we can guess quite easily what is the mu z operator should be. So in matrix form, this should be just a matrix of 1, 0, 0, minus 1. So you can check quite easily that if you take this operator and you apply on this eigenvalue, then you get the eigenvalue plus mu b. And if you take this operator and apply this on the minus z eigenvalue, you will get the eigenvector minus, you will get the eigenvalue minus mu b. So this is a simple expression to describe the result that we have in the experiment. Okay, that's the simple, still even on the level of the guesswork, how to describe this experiment in the language of quantum mechanics. So remember that we are talking here about a different Hilbert space, right, than what we had in the last week, right? So last week the Hilbert space that we talked about was related to the coordinate x, y, and z, right? Here we have a different Hilbert space. This Hilbert space is only of the size of 2, because this is what we see. So what happens in the experiment, there are two spots. So the Hilbert space is not related to x, y, z, so it's a different Hilbert space, and the size of the Hilbert space is 2. So essentially, this is just an additional information about the system, and it should be a tensor product with the wave function that we created a week ago, right? So now we are talking about a different degree of freedom of the system. So now another experimental fact. So now let's imagine that you take, so now after the first time you are going through this apparatus, you get 2 spots. Now the question is, what will happen if we now take the second apparatus after transferring the atoms through the first one, and then we take this apparatus and rotate it, right, along, instead of z-axis now we rotate along the x-axis. What we will see? Okay, again, right, so we have a beam of atoms, right, that goes like that. So after going through this apparatus, we know that this beam is split into 2. Right, there is a 1 and there is a second one. Now let's suppose that one we block. Suppose that we block the lower one. There is only upper one that goes forward. Now it meets on this direction, on its propagation direction, the second apparatus like that. But instead of making this apparatus oriented in the z direction, by the way, what happens if you oriented this apparatus in the z direction? What then happens? Will it split into 2? No. Okay. So we will. That's we agree, right? So we apply once we apply this operator on the eigenvector, we get eigenvalue like that. So this is the only now state that we have in the system. So if we apply again this matrix on this eigenstate, we will have again the same eigenvalue. So there will be only one spot, right? So everything is aligned along the plus z-axis, right? So now, but the question is different now. If we have this apparatus, now we rotate this apparatus in a direction which is equal along x-axis. Then what happens? Do we see 2 spots or 1 spot? We'll see 2 spots. So that's, you can consider as an experimental fact, right? So you don't need to guess even, but knowing the quantum mechanics, you can guess that actually there is nothing happens in the x direction because everything happens before only in z direction. So in x direction, we did nothing. Right, yeah. So in order to get the, so this is the operator, right? So this is the eigenvector, and this is the second eigenvector, and this is eigenvalue. Right? So this means that if I take the operator mu z and multiply this on the eigenvector plus z, I will get plus mu b multiplied by eigenvector z. Oh, you mean you want me to? Yeah, yes. That's right. You are right. Yeah. So now we are getting how to describe this experimental fact that we actually, when we once going through this apparatus and then we rotate this apparatus, we get again 2 spots. So this should be described by the fact that actually its expectation value of the mu x apparatus, so sorry, mu x operator, so this is expectation value of this mu x operator when we apply vectors, eigenvectors in z direction, either plus or minus this should be equal to 0, right? This is just because we because we obtain again two spots, right? So there will be equal probability to find this with the value of plus mu b or minus mu b. So the expectation value of this mu x operator should be equal to 0. That's how to describe the experimental fact. So now we want to find this matrix. So this matrix mu x that will answer this question. So this matrix will be equal to mu b multiplied by some general matrix of ax, bx, cx, dx, right? So we have to find these values. So we know that this matrix should be Hermitian. Therefore, ax and bx and dx, right? So these elements, the diagonal element, should be real, and also the cx and bx should be complex conjugate to each other. So cx should be equal to complex conjugate dx. So this is just a requirement of the Hermitian matrix. Now, in addition, so we know that we can so if we so we know that the eigenvalues of this operator should be either be plus mu b or minus mu b. So the sum of these eigenvalues is equal to 0, right? So the sum of eigenvalues of the operator can be described by the mathematical requirement that the trace of the matrix of mu x should be equal to 0. So it's ax plus dx is equal to 0. So this is the requirement that the sum of eigenvalues of the matrix will be equal to 0. And so that's the same sum of eigenvalues. This is the another requirement. And in addition, there is another requirement is that the product of eigenvalues, right? So we have some eigenvalue lambda 1 and lambda 2. So, but we know that the product of lambda 1 multiplied by lambda 2 will be equal to, according to this simple 2 by 2 matrix, is just ax dx minus cx bx, right? So this is just determinant of matrix mu x. This should be equal to minus 1. And we also have this requirement that the expectation value is equal to 0. Okay, now so this is just a requirement of lambda 1 plus lambda 2 will be equal to 0. So now we are actually looking for a certain matrix that will answer to this requirement. So, and if you try to find such a matrix, the only possibility would be to write the matrix which is equal to mu b multiplied by 0 e to the minus I phi x, e to the power of I phi x, and this is 0 on the diagonal. So the only matrix that will answer all these requirements can be of this general form. So it has to be 0 on diagonal, and off diagonal we have some phase, right? It's this matrix produced. So this is just a general considerations out of a simple experimental fact. So we're still describing some experimental facts, and based on these experimental facts, we are able to write down this operator of the mu x. In addition, what we can say is that if we do now, instead of rotating the operators in the x direction, we can try to rotate this operators in the y direction, and we can understand that there will be the same result. So there will be the same requirements for the matrix of mu y. So there will be also guess that the mu y should be equal to mu b multiplied by zeros on diagonal, but there is a different phase can be. So this different phase we can mark as e to the power minus I phi y. And there is a e to the power of I phi y. So now we have two matrices, right? And in order to finally define what are these matrices, we have to define what is the phase phi x and what is the phase of phi y. That's what we need to do. Okay, so now in order to describe that, we can actually say that we know that if we apply or if we look for the expectation value of operator mu y on the eigenvectors of operator x, this should be equal to 0, right? So that's the same more or less situation that we have here, that the eigenvalues in z direction, the expectation value of mu x is equal to 0. So the expectation value here of the mu y operator is also equal to 0. So now we can write what is the x, right? So what is this x value? So this plus eigenvector can be written as 1 over square root of the vector plus in z direction plus a certain phase I phi x into the multiply by the eigenvector minus into the direction of z. So that's the most general form of the vector plus in x direction. So now if we take this vector and we apply it onto mu y matrix, like, and we look the expectation value using this eigenvector, we will find that essentially this value of x plus mu y plus x is actually equal to mu b multiplied by cosine, the difference between the phase phi x minus phi y. That you can easily check. Now we have to take into account this consideration. So the expectation value should be equal to 0. But from the other point of view, taking this vector with a general phase, we can come out to the conclusion that actually this expectation value is a cosinus of this phase difference. So in order to get this equal to 0, so we have to require that the phase phi x minus phi y should be equal an integer number of pi over 2. Pi over 2. So it can be some modulo of pi over 2. Now this is the only requirement that we have. So we don't have requirement, a specific requirement regarding the phi x independent of phi y, but we know that difference between phi x and phi y, the difference between these two phases, should be equal to pi half. So now we can just suggest that phi x will be equal to 0, then phi y will be equal to pi over 2, and then we can finally write down these matrices according to this analysis. So this matrix will be just the matrix of 1 and 1 off diagonal, and the matrix of B of Y will be minus I and I off diagonal. So of course what we get here in this story, so if we combine these operators, the operator according to mu z, this is the operator of 1 minus 1 on diagonal, and mu x and mu y, this is 1, 1 and minus I off diagonal. So you recognize immediately that this is Pauli matrices. So we've got these Pauli matrices out of the analysis of the experimental results of the Stern-Gerlach experiment. So you got this formalism out of, requirement that experiments describe you. So this is the experimental reality, which is described by these matrices. And now we can actually, of course, say that these matrices are non-commutative, so we have a general commutational relation between these matrices, but this is something that you know very well. The commutation between the matrix I and J is equal to 2I mu B mu K, where the mu B is the Magneton Bohr, and mu K and K, I, J, and K, these are just X, Y, and Z. So this is general property of Pauli matrices. So now the question is actually, it's now this is the most interesting question out of this story. So we know that there is some so we know that by measuring some direction, right, in z direction, for example, if we measure, so we perturb the x and y directions. So this is we know because after measuring the z direction, we can actually go and rotate our apparatus and see that x and y will split into two spots, right? So let's imagine the next type of the experiment. So you start from this z direction. So you split, you go and split your atomic beam in two spots. Now you block one spot and only one continue. Now what you do? You rotate the operators along the x direction, and you go again through these operators, and you know that there is a split into two spots. That we already know. Now you block one of the spots, and you rotate your operators again back to z direction. So there are 3 times you go through the apparatus. First one along z direction, then along x direction, and then you come back to z direction. So coming back to z direction, so now the question is, what do you get? 1 spot or 2 spots? You get 2 spots, okay? So you got 2 spots, so this means that measuring on x direction actually disturbed the information that we already imprinted measuring into the z direction, right? So this means that measuring in one direction, so this is exactly this information is written here, right? So this these 3 matrices are not commute with each other. So this incommutativity of these matrices actually means that we perturb measurement in x direction if we measure on z direction, and it's perturbed the z direction if we measure on x direction. Now the question that I want to ask now is, how do you understand that? how we can understand this fact. So let's imagine a simple story. The simple story tells something like that. So we know that according to semi-classical picture, or classical picture, not the semi-classical, completely classical picture, we have a magnetic moment that rotates, right? So we have a z direction, and we have a rotation of our precession of our magnetic moment. So if the magnetic moment persists, so that's exactly what does this mean, right? This perturbation on the x and y direction. So according to z direction, we have a certain direction, but according to x and y direction, the magnetic moment rotates like that, persists. So the projection on x and y axis actually rotates. So this means that if we measure something along z axis, we actually affect the x and y direction because of this precession. So this is a classical picture of what it's saying to us. So this means that, of course, we don't know where we will finish, right? So we start at certain direction, to certain projection on x-axis. So but this projection will be changed due to the fact that we go through the apparatus and we persist along z direction. So the projection on x-axis will be changed. That's what classical picture says. Okay, is this a really classical effect? Right? So no, this is not a classical effect. Why it's not a classical effect? Because I can imagine how to treat the system in such a way that I will trick it. How to trick the system? So I can imagine putting this apparatus exactly as long as the integer number of the rotations of the spin around the circle, right? So if I start, for example, along this x direction, there is a certain value along this x direction. So now I start the precession, and now I actually go out of the apparatus exactly at the position where the projection on the x-axis will be exactly the same. So this means that I'm just taking the apparatus at a certain length, right? And this, I cut it at a certain length, and I know that after going with a certain velocity along this length, I will end up with the same projection on x. So I do not perturb the x direction according to classical physics. Does it work? No, it doesn't. Okay, so this is a really quantum effect. So this quantum effect, in order to understand this quantum effect, so we have to actually consider, in order to explain how it works, we had a, sorry. Okay, that works, big.
Can't do single full integer for all of them. It's not statistical.
Yeah, well, suppose you work with a single spin.
Okay. But you are not talking about classical closure, you're talking about quantum closure.
Well, I still can still isolate a single atom, right? So I work with a single atom only.
Single atom, not single spin.
Well, yeah, that's the idea, right? So when in this context, when I talk about the spin, this means that it's a single atom. Okay. So I can, this is what the story tells you, right? So I can actually align, right? So taking the apparatus, aligning it in the x direction, and I can align in certain direction, right? So I know where the direction is. And now I apply the z direction in certain lengths, okay, right? And now I apply the x again. What do I see? Do I see a single spot or two spots? So I did exactly the scenario that I know initial value of in this x direction. So I projected it in the x direction. And now I know that now I know the velocity of this atom, with good precision, suppose. Then
Can you tell the velocity of the atom?
Well, imagine that you can cut this apparatus quite flexibly, looking for a certain, match between this. So what I want to say is that whatever you do in this experiment, you will never get this type of trick to trick the experiment, right? So that's the idea. So I mean, I want to say that there is no classical physics here, so we have to apply the quantum mechanics. And the quantum mechanical requirement that will explain this effect will be that we need to satisfy Heisenberg uncertainty principle. Okay, that's the idea. That this is what I want to describe quickly. So. So we know that according to Heisenberg uncertainty, delta z, delta p, along the z-axis should be larger or equal to h bar up to half. Now what we are saying is that in order to get a good resolution, right, in this story, so this spot has a size, certain size, right, in this z direction. So this is delta z, right? So in order to get a good resolution in this experiment, you really need to separate these two spots at a distance which is larger than the size of the spot itself, right? Otherwise, there is no meaning in the measurement, so you cannot separate these two values. So what does this mean? This means that we have to apply the force in such a way, so the force, the Magneton bore multiplied by the gradient dB z according to dz, so that's the force, multiplied by time, that's the momentum. So this guy should be much larger than the delta p z initial, right? So initial delta p z actually causes us, so the distribution of the initial atoms in the z direction, so this is z direction, so initially atoms do not go completely parallel to each other, so there is a certain distribution of the momentum in z direction. So this actually causes the finite size of the system. So t is the interaction time. So what is the interaction time in this story? So that's the force multiplied by time. This gives me the momentum. So this momentum spread should be much larger than the initial momentum spread. Otherwise, I'm not distinguishing between these two spots. Okay, that's one requirement. So from the other point of view, there is a finite size in delta z, right? And this finite size of delta z that we have initially, so we are here now we are talking about delta pz in this direction, delta pz, but there is also initial delta z, the size, the spot size. So this spot size says us what is the difference of the gradient of the magnetic field that atoms will feel when it enters into the apparatus, where they enters into this apparatus. So these atoms actually are very different, right? They feel different magnetic field along z-axis. So if they feel different magnetic field along z-axis, so they will feel a different force, and that will cause a different delta z at the end. So this means that there is a different Larmor frequencies, right, in the system. So different atoms feel different magnetic field. There are different Larmor frequencies in this story. So remember that we want to know the Larmor frequency in such a way in order to bring the projection exactly at the same position where it started to, but there is a dispersion of this initial position, and this dispersion actually causes the spread of the of the Larmor frequencies. So in order to get the positive result out of what we require, we want to have this spread to be much smaller than the initial spread of delta z, or in such a way that we actually want that the difference in these Larmor frequencies, right, these differences in Larmor frequencies, which is equal to mu b divided by h bar. This is how we define the Larmor frequencies here, multiplied by the gradient of dBz dz multiplied by delta z, right? So that's the difference of the Larmor frequencies. So this difference multiplied by interaction time. So what we require is that delta omega L multiplied by the same interaction time should be much smaller than the 2 pi. This is the requirement. So these are, right, different Larmor frequencies of different atoms due to the initial spread in size. And if we do not get this requirement, so if this spread is not much smaller than 2 pi, then we will always perturb the x and y direction. Is that clear, or shall we say more words about that? This requirement. So now everything else is just simple math, because now we can get this distribution of the Larmor frequencies into this requirement, substitute this expression into this requirement. So we get mu b divided by h bar multiplied by the gradient of dBz dz multiplied by delta z multiplied by time. This should be much smaller than the 2 pi. So now we can get rid of the story of delta bz dz. This is what we want in this size, right? So look here. This is the value of the momentum. And we have exactly the same here. So we get, therefore, the magnetic moment mu b multiplied by dBz dz multiplied by multiplied by t. So this I have on the left side of the inequality. Here from the right side of the inequality, I have 2 pi h bar, 2 pi h bar from here, and divided by delta z, right? Divided by delta z. So now if I take a look here to the requirement of Heisenberg uncertainty principle, so I can just exchange, right, delta z with h bar divided by twice delta pz, and this will be even stronger, the requirement here. So it's still even smaller than the delta pz 2 pi h bar divided by h bar multiplied by 2, right, multiplied by 2 delta pz. Okay, so you see what's going on here. Here h bar is falling apart, so up to a certain factor of 4 pi, we get actually a contradiction in two requirements. From one point of view, this spread in the momentum should be much larger than delta pz. From the other, we require that this spread in the momentum should be much smaller than delta pz, multiplied by a certain factor. But much smaller means it's much smaller. So we have a contradiction between these two requirements. So this should be from one point of view much larger than that. From that point of view, this spread of the momentum. From the other point of view, this spread of the momentum should be much smaller than stand value. So this means that it will never happen. So whatever you will try to do in the experiment, you will never be able to treat the system in such a way that you will be able, right, to obtain a single spot after you measure some direction. So, which means that we really understand what is the meaning of that these three operators are non-commutative. So this means that if you measure in one direction, the other two directions will be perturbed. There is no other possibility. So whatever you do, you will always see two spots if you rotate your apparatus in the other direction. And this is also agrees with this treatment, and this agrees with satisfaction. So we have to satisfy the Heisenberg uncertainty principle, and if we need to satisfy the Heisenberg uncertainty principle, we have some contradiction in trying to treat the system from the point of view of the classical system. Well, this means that you know how the answer of this experiment will be, and this is indeed the case. So whatever you do in the experiment, measuring one direction, perturb the other direction. So now, this Stern-Gerlach experiment is, as I said, is a real sort of a pivotal point in the history. That was the first demonstration of the quantization of angular momentum. It was later understood as a spin of the electron. We will take again look at the Stern-Gerlach experiment later in the course. It will help us to understand when the wave function should be exchanged with density matrix. But now we will try to go forward and say, okay, so we have a spin of the electron. So where it comes from? Right? So what is this strange feature it is? Right? So this sort of an additional degree of freedom that comes from nowhere. So we still can understand that there is a certain magnetic moment which is related to any angular momentum, but the spin of the electron is not the angular momentum, right? So it's an additional degree of freedom. So the breakthrough actually in the understanding of the spin of the electron comes from the Dirac theory. So the Dirac theory is a theory that takes not a Schrödinger equation as an equation that describes the system, but it actually considers a relativistic Klein-Gordon equation in order to solve the system, which is a relativistic system, right? So we know that the velocity of the atom inside the velocity of the electron, the speed of the electron inside the atom is quite, well, you can call it slow, but it's still far from being close to speed of light. That's true. So there is a fine structured constant that actually relates between speed of light and speed of the electron on the ground state of the orbital in the hydrogen atom. And this factor we know that this is 1/137, so it's sort of a small correction, right? So this relativistic effect. But this small correction is important, and this small correction is only of the order of 0.1%, right? So it's only of the order of 1.1%, but they remind you that they should tell you every single time we met that we are talking about precision measurement. So it's precision. This is the key word in atomic physics. So we cannot just throw away this effect and say, okay, it's too small not to look at it. I should say that this is huge. If we start to do experiments, if we don't take into account anything related to relativity, then we will miss everything regarding the spectrum of energy levels. So then the idea is just to take a relativistic equation and solve it and find the eigenenergies and eigenvalues according to Stern-Gerlach equation, or equation which actually takes into account time and energy and the momentum in the same order. But the problem is that this is sort of, well, that's something that should not be, well, they're largely enlarged. The atomic physics is non-relativistic, or at least what we are talking here from the atomic physics, about the atomic physics, largely non-relativistic. So we are talking about some small energies, but this relativistic correction is important, the fine structure constant or fine structure splitting, so we have to take into account this relativistic effect. But this is more or less the only thing that we are going to do with relativity. So, and dealing with Dirac equation and solving the Dirac equation is not a simple task. Okay, and it should not be actually part of just some distinguished parts in the atomic physics course. It's just a start of the whole story of field theory, and this is where it should be actually thoroughly treated and understood the solution of this equation. So it's not a simple task. Okay, so the solution of Dirac equation is not a simple mathematical task. What we will do at the end, so we will sort of skip, right? So we'll sort of skip this solution, and we will go to write some terms that arise from the solution of Dirac equation into the, and we'll put them into the Schrödinger equation. So this will be a small perturbation for the Schrödinger equation. But before we do that, so it means that we actually, sort of do not say anything about the Dirac equation. Something I do want to say, so at least in the context of speed. So this is the result of the solution of a Dirac equation, that the wave function is not single component wave function. So up to now, let me remove all this story from the board. Up to now, we talked about, this last week, we talked about Schrödinger equation. We solved the Schrödinger equation. And found eigenvalues and eigenvectors. So this describes the orbits of the electron and wave function of the electron. But this wave function depended only on x, y, and z, so only on the coordinate. Right? The problem is now that the question is, if this is the only thing that we have in the world, so where the spin in this story. So the spin comes from the solution of the Dirac equation. So the Dirac equation, when you solve it, and the amazing fact is that solving solution of the Dirac equation is also analytical, so you can analytically solve it, which is quite amazing. But if you solve it analytically, you get to the conclusion that the wave function cannot be single component object. So, and this is exactly where the spin pops up into the story. So the spin is not something that we have to plug into the story phenomenologically. This is what we do usually in atomic physics. But it's not a phenomenological effect. It's an effect that comes from the fact that you have to solve relativistic equation. This relativistic equation is the Dirac equation. Solution of the relativistic equation requires that the wave function is not single component wave function, but there are several components for the wave function, and not even two, but actually 4 components. So that's the minimal solution of a Dirac equation. It shows that you have to do at least 4 component wave function in order to solve this equation. So I'll briefly show you how it goes. So it's just for general information. Strictly speaking, we are not going to develop that further, and it will not be a part of general way of the course. But in some sense, I do want to tell you about that, at least for those who still didn't meet the story before. I will bring it back after that. So in a sense, what I'm telling you now is again, some sort of a general consideration. It's not something that we are going to develop. Still, what we need to do is to solve a relativistic equation. The relativistic equation is the equation that takes the time derivative in the second order. It's a second derivative in time as well as the second derivative in space. Right? So it's E squared equal to mc squared squared. That's the energy plus pc squared. Well, this is sort of an energy equation that should be, so we should apply to the wave function. So this is the operator, and we have to find the wave function. This is the free, by the way, free electron, right? There is no interaction. This is not the electron inside the potential, so there is no potential energy here, only kinetic energy, and the energy which is related to the mass, right? So that's just the free electron equation. So, and now you have to solve this equation to find eigenvalues and eigenvectors. Well, this equation known as the Klein-Gordon equation. This was actually the beginning of the story how Schrödinger tried. So Schrödinger tried actually to solve this equation. There is a problem with this equation. This equation gives you negative energies, so you don't know usually what to do with these negative energies. And this is exactly what actually stopped Schrödinger from dealing with this equation. Right, non-relativistic equation. The Dirac sort of was successful in finding non-trivial solutions to this equation. So this equation is not simple. So again, this is just a free electron, no atom, no column interaction. So to solve this equation with the interaction, this is just an additional task. The idea that Dirac came with, right, that was sort of strange. Right? You wouldn't come with this idea that simple. Right? So the idea is that the equation, right, so this is just the energy, and the equation to find the eigenvalue and eigenfunctions takes into account the second derivative in time, multiplied by the psi, that's the wave function, and then mc squared multiplied by psi minus theta squared c squared, second derivative in space, psi. That's a free electron. Free electron Klein-Gordon equation. So this has to be solved in order to solve the relativistic problem. Now, the idea that Dirac came with was sort of strange. He said, I don't want to solve this equation, right? I want to solve the equation of the first order. instead of second derivative in time and in place in the space, let's write the equation, which is the first derivative in space and the first derivative in time. So still, as relativistic theory requires, so we have to take time and space in the same footing, right? So this is the same. That's the difference between relativistic equation and non-relativistic equation. But the true equation is the second derivative in time. So actually Dirac wrote a different type of equation. He said, okay, this is the Dirac equation. He said, okay, let's take IH bar d dt psi is equal to C multiplied by alpha multiplied by P operator plus beta mc squared. This is the Hamiltonian. This Hamiltonian is applied to the wave function of psi. That's the Dirac equation. So there is no simple way to explain why this equation should be interesting. So this is just a crazy idea of a crazy man that actually was extremely successful in delivering so many interesting messages trying to actually deal with this type of equation. So this is the Dirac equation. This is the true equation. Right? So we do not really need to find the wave function that satisfies this equation. So this equation is problematic. It's not true. It's not physical because it does not satisfy Lorentz invariance. So this equation is Lorentz invariant, and this equation is not. So there is no reason to solve this equation. But what Dirac says, so there are some objects here. So this alpha, for example, it's an object. It's not a number. It's an object, right? So beta is another object. So you don't know what these objects are. And this is the idea of Dirac. This is the brilliant idea of Dirac. He said, okay, let's not write some simple equation. Let's try to find some non-trivial solution of this equation. In order to try to do non-trivial solution of this equation, let's try to write this equation and put here the multiplication, and then put here some object which will multiply the kinetic energy, and some object that will multiply the mass energy related to the mass. And then what we want to do is just actually to take this type of equation and find what should be this object and this object in such a way that this equation will, that this wave function will satisfy also the true equation. So the idea is, of course, to find the wave function that satisfies this equation, but we do that sort of in a different way by trying to find some type of what these objects are. So it's something that is not very simple to do. I will just drive a simple, some few lines that I'll try to explain how to get to the idea of what this alpha and beta should be, okay? What sort of objects they should be. So in order to get from this equation to this equation, you actually need to take this equation, multiply it by the same equation once more, right? To get the second over here, to get the second over here, to get the second over here, you have to multiply this equation by the same equation. So this is what more or less is done. So the idea is that the energy minus, so this is the eigen energy that we want to find, minus C multiplied by alpha multiplied by P operator minus beta mc squared. This walks on the side should be equal to 0, right? So if we are sort of, if this is the eigenenergy, then this is the Dirac equation written in a different form. So now I want to multiply this equation on another equation, which is essentially the same, that with plus sign. C alpha P plus beta MC squared. So if we do that, we get the following equation. Well, remember, alpha is not a number, beta is not a number, it's an object. So and multiplying between these two guys is not a simple task, right? So the only thing which is simple here, that is multiplied the E, right, which multiplies this and multiplies this, will be cancelled towards this E multiplied by this and multiplied by that, because they are different signs. So it's the idea to drop out the E multiplied by these two terms. And now if we do that, so this should be E squared. This is what is left from multiplication of E on E. So it gives us the second order here. E. Now we get the following. So now you are invited to check these calculations. It's C squared multiplied by bracket sum. Now I have to take the sum from 1, 2, 3. So now alpha of the I into the second power multiplied by pi to the second order. So this is the multiplication of p on p, right? That gives me this guy. So, but this is not the only way where p is right. So now there is another complex term with I and j, and I should be smaller than j. So here I have to multiply alpha I, alpha j plus alpha I, sorry, alpha j, alpha I. And this is multiplied by pi, pj. Now, this is still comes from the multiplication of these two terms. Right? We just take into account that alpha is not a simple object, but something different. Right? It's not a simple number, so it's a certain object that we want to find. So now, it's still we still have something that will come from multiplication of this term on that one, and this term on that one, this term on that one. So this gives us an additional term. So here the bracket is closed, so c squared is multiplied on that. So this is the term, this term. And now I have an additional term minus mc cubed sum over I from 1 to 3. Now it's alpha I multiplied by beta plus beta multiplied by alpha I multiplied by pi bracket. So this part comes from the multiplication, right? You can see it immediately. From this term multiplied by that one, and from this term multiplied by that one. Okay. So the only thing that is still left is the multiplication of these two terms. So this gives me m squared c to the 4th power beta to the 2nd power. So now all this is the operator that is applied to the wave function, and this should be equal to 0. Right. This is, yeah.
Why do we assume that E commutes with alpha and beta?
Well, E is a number. That's the energy. This is just the eigen energy. This is a number. Like an energy, so energy is just a number. So now what we are saying is that this equation is a crazy one and is not the correct one. The correct one is this one. So now what we want to do, we want to find the solution of this equation, but only when this equation will collapse into this equation. So in order to collapse this equation into this equation, we have to require something on this exactly object, alpha and beta. Right? This is what is required. So in order to go from here to here, right, you know that this we have to keep. This is the second order in momentum. But this guy, we don't need it. So it has to be 0, right? So then we know that this guy should be equal to 0. And then we know that this guy should be equal to 0 because this is not also not a part of the equation. So this gives us certain requirements in order to find what the object alpha and beta should be. So it means that alpha, so all the requirements means that alpha 1 squared equal to alpha 2 squared. This is because here we have alpha 1 squared, but here in this equation we have only p squared, c squared. P squared, c squared is here written. So it means that we need all these guys equal to 1, alpha 3 squared, if alpha is sort of a vector object. And now it should be equal to beta squared. It should be equal to 1. Then it will be okay. And also, we need to take care that this is will be, so this sum will be equal to 0. So this sum is not a commutative relation, it's anti-commutative relations, right? So we can write them as anti-commutative relations like that. So alpha 1, alpha 2 is equal to alpha 2, alpha 3 is equal to alpha 3, alpha 1. And this should be equal to alpha 1 beta equal to alpha 2 beta, and this should be equal to alpha 3 beta. Okay, now all this should be equal to 0. Now, if these guys can be satisfied together, then we can take this equation and reduce it to this equation, right? So in here, this is the brilliant turn in the story. Because based on these requirements, you can actually say what the object alpha and beta can be, right? And it's turned out that in order to satisfy all this story, so the object alpha has to be a matrix 4 by 4, and this is the minimal size of the matrix that can be taken in order to satisfy this story. So this, otherwise it doesn't work. Right? That's the brilliant term in this story. So trying to do something completely crazy, you come to a very interesting conclusion. And this interesting conclusion says that your object, alpha and beta, has to be something which is which is equal to an object, which is 4 by 4. So I'm writing here a big 0 because it's 0, 0 and 0, 0. And here it's a sigma I and sigma I, which is the Pauli matrices. Okay. So Pauli matrix is 2 by 2, and here 2 by 2. Here 0 is also 2 by 2 and 2 by 2. So this is 4 by 4 object. And then a beta is also a matrix 4 by 4. So this is sort of a matrix, a unitary matrix, and the minus unitary matrix. And this is big 0 here and here. So this is the on diagonal, 1, 1, minus 1, minus 1. And this is off diagonal matrix. So this is what you get, and sigma I is the Pauli matrices, sigma x, sigma y, sigma z. So this alpha has three components. It's a three-component object, right? Alpha. It's a sort of vector, but each component of this vector is a 4x4 matrix. That's the story. Well, it's not an easy story, right? So you have to be Dirac in order to derive that, and to get to this conclusion. But what you get after realizing what is this, right? So realize immediately that this equation actually, the solution of this equation should be a wave function that is not a single component wave function, but a wave function that is multiplied by the matrix of 4x4. Therefore, there is a 4-component wave function that solves this equation. Right? So the wave function that solves this equation should be psi1, psi2, psi3, psi4. Each of this psi is the wave function, right? So it's a wave function that we found solving the Stern-Gerlach Equation a week ago. So each wave function has its x, y, and z components, but there are 4 different wave functions that we need, four different components for this function that we need to satisfy this relativistic equation. So now it's a long story. So again, I'm not I'm not going to take this story and continue to the direction that we want. 4-component is not even spin, right? So because spin has to have only 2 components. So this is too many to having the spin. So we have to get rid of 2 components. And actually, in order to get rid of these 2 components, you actually need to take the limits of this equation and to develop the limit of this equation into the non-relativistic case. So when the velocity is small, then you can actually develop this equation into the limit of the non-relativistic one. And solving this limit, you can show, so I'm not doing that, but you can do that. One can do that. That when you go into the non-relativistic limit, these 2 components actually are very small as compared to these 2 components. So there are 2 components that are very large, and there are 2 components small. So then you can actually, in non-relativistic limit, you can neglect these 2 components, and you say that your wave function has only 2 components. That's more or less how stories goes. And then getting out of this whole relativistic story, we actually end up with the Stern-Gerlach equation. But this Stern-Gerlach equation now requires 2-component wave function, not 1-component wave function. Again, the Stern-Gerlach equation is only for the wave function which depends on x, y, z. But now, as a heritage from the Dirac equation, we have to solve this Stern-Gerlach equation for 2-component wave function. And this 2-component wave function has the same x, y, z coordinates. So it's exactly the same wave function because the Stern-Gerlach equation do not have this 2-component wave function. But this wave function has to be different by something from each other. Otherwise, it's trivial, right? And so the difference of these 2 components from each other is exactly the difference of the presence of the spin. So this says that there is an additional quantum number in the story, and this quantum number is spin. So this is not the only heritage of the Dirac equation into the Stern-Gerlach equation. So not only 2-component wave function left, there are also something that left for the Hamiltonian. So the Hamiltonian is not only the kinetic energy and the potential energy due to the Coulomb interaction, but there is an additional terms that are factors of p. That are factors of alpha squared. Right? So alpha, if I remind you that alpha we wrote is the velocity of the Bohr orbit, of the electron on the Bohr orbit divided by the c, divided by the speed of light. So, and the correction to the Hamiltonian so this is p, right? right? So this is the correction of the P. The correction of the P squared should be alpha squared. So this is the order of the corrections to the energy, or to the Hamiltonian in the case of, in the limit of non-relativistic energy. So we expect to have the corrections in the Hamiltonian that will be of the order of alpha squared. So there are small corrections, because alpha is 1 over 137, right? But if you develop your relativistic energy, right? So this relativistic energy, if you develop it into the limit of non-relativistic case, in the Hamiltonian we will see additional terms, and these additional terms should be of the order, so for the first order correction in this effect, they all should be of the order of alpha squared. So this is how it goes. So it should be developed in the limit of, in the non-relativistic limit, the relativistic energy should be developed in the power of alpha squared. And the first order in alpha squared will be the corrections of the first order of the relativistic effect. So it can be done. It's not easy. I'm not doing that. It's not an easy math, but we can actually come to the conclusion what is the correction to this Hamiltonian of this order. So there are 3 terms in these corrections, and these 3 terms actually have one of them is the correction due to the spin orbit. So we will take these terms one by one, and we will calculate the shift of the energy due to all these terms. Just the only last probably comment on the story of Dirac equation. So the interesting thing is that, of course, so the Dirac equation, this is interesting really, because this Dirac equation can be solved analytically, which is sort of non-trivial fact. You can analytically find the energies, you can analytically find the wave functions, and you can also come to the conclusion that L, the angular momentum, is not a good quantum number anymore. So the angular momentum is not a good quantum number because there is an additional degrees of freedom that comes out, that comes into the story. This additional degree of freedom is the additional components of the wave function. And this additional degree of freedom actually is the spin of the electron, right? So we have the orbital angular momentum, but in addition to that, we have a spin of the electron. So in this spin of the electron is an additional angular momentum. So as usual in quantum mechanics, we have to solve the equation in case of sum of both. And then for this equation, actually, the angular momentum is not a good quantum number. The good quantum number will be the sum of the angular momentum plus the spin of the electron, which is a new quantum number. This is the quantum number of J. And we will see how it comes into the story when we start to treat each one of these additional terms into the equation. Okay, so that's more or less the story. So again, I'm sorry I'm not going into the story of the Dirac equation. I think it's not the correct platform to do. So the Dirac equation is the starting point of the field theory, where this is where the field theory started, and this is usually the course on quantum field theory starts by the Dirac equation and goes forward using it. So we are not going to use the Dirac equation in any way. So this is the reason why I'm skipping it completely, and I'm not the right person to do that. Also, to introduce you into the world of the quantum field theory. What we are going to do is we are going to use quantum mechanical treatment of the additional terms that comes from the relativistic equation into our known Schrödinger equation that we had until now. So you will have to believe me that there are only 3 terms of the relevant order. So this you will have to believe me. Now, the relevant order of alpha square has only three different terms. So in all these three terms, we will sort of pinpoint of the origin of this correction. Okay, so this is what we are going to do now. After this nice story about Dirac Equation. So this was the Nobel Prize winning theory. It took only several years, something like 5 years between the Dirac equation and Nobel Prize to Dirac. And the reason it took only 5 years was actually the experimental proof that the Dirac theory is correct. It's quite funny because we are going to write actually now some corrections to energy levels of atoms, which are totally correct. So you can come and calculate and measure them, and you see that they come from the Dirac theory, but this was not correct. So the problem of the Dirac theory was that these 4 components actually predict something additional. So it predicts the existence of a positron, which is the electron with the positive charge. That sounded completely crazy. So nobody really believed that this can exist. So but it was actually measured in the experiment only a few years after the prediction of Dirac. And this is an additional, and these are positron and these 2 additional components of the wave function. So this 2 wave function is the electron, and 2 components, additional components of the wave function is actually the positron. So you see that this is the whole story. So it's a complete story, quite a big and quite interesting. So you should find it in another place. So let's do a simple, less complex story. So let's write now the Hamiltonian that we have. So we have the Hamiltonian, which is now with relativistic corrections. So and we call this Hamiltonian the fine structure Hamiltonian, FS, fine structure. So the reason we call it fine structure Hamiltonian because this is not the whole story. So we are taking into account some corrections, which are order of alpha squared. This is not the only corrections in the world that we will have to consider. So for example, after considering fine structure, we will go and consider something else, and we will have some additional terms in the Hamiltonian. So right now, we have H0. This is the Hamiltonian that we had already last week. This part has into it Coulomb interactions. Now, in addition, we have, no, it's not here, because this should be here, right? So this is the correction to the H0. So the fine structure is a correction to H0. So this fine structure has 3 terms, as I promised. One is the term that corrects due to the kinetic energy. Okay, so this is the correction due to the kinetic energy, due to this term. This one, p squared term. And we will see how it comes. Now the second one is the spin-orbit coupling. This term comes from the coupling between the spin of the electron to the orbital motion of the electron. This also gives the same order correction to the Hamiltonian, plus the Darwin term. This is the third one that we will consider. So there is a Darwin term that we will talk about at the end. So let's start from the first correction. This first correction is the H relativistic. So this one is relatively easy to understand. So what is the kinetic energy that we have? So the kinetic energy that we have is kinetic energy of the story from the relativistic point of view is equal to the total energy minus the energy which is related to the mass of the mass of the object. So this is the free kinetic energy, right? So this is total energy in the basket. So now, what does this mean? This means that if I'm writing now the mc squared plus p squared c squared square root of that, this is the total energy, minus mc squared. That's from this total energy, right? So we have here this part. So now we are taking the limit where the p is much smaller than, well, not the p, but the b is much smaller than c. Okay? So then we can develop this part into the orders of the small parameter. So we get here the following. So this is the mc squared. We get it outside. Mc squared. Now it's 1 plus 1/2, right? So we take the mc squared out, squared. Then it's 1 plus 1/2 of the pc squared divided by mc squared. Sorry, pc divided by mc squared into the second power squared. That's the first correction of the opening of the square roots, minus 1/8 pc divided by mc squared to the fourth power, and so on and so forth. So others we don't need. Minus 1, and this minus 1, it comes from here. So 1 and 1 is done out of the story. So what we get here, we get here equal to, so this goes with the 1 power, then we get 1/2 of p squared divided by m. That's the first term. And this is the kinetic energy, right, term, as usual, in the non-relativistic limit, right? If we neglect all other corrections of the higher order, that's what we have in our H0, so it's not interesting term for us. This term is already in H0. But the next one is minus p to the fourth power divided by 8, m to the third power, c to the fourth power. That's the correction of the first order correction to the non-relativistic kinetic energy due to the relativistic effect. Okay, so essentially, this is what the non-relativistic part. So this is the H relativistic is actually written there. This means that we essentially have here minus p to the fourth power divided by 8, m to the third power, c to the second power. So that's the correction term that we have to calculate. Okay. So now, how we do that? So this is so we use for those of you who are familiar with second quantum mechanics. We do that by just perturbation theory, because this is a small correction. So we just do it first order perturbation theory. For those of you who is now on the, I'm not sure that I know if there are people from the first. So those of you who only knows about the first quantum mechanics, so perturbation theory is probably not taught yet. The quantum mechanics too. But you will be hear about that next week. Okay, so that's missing sort of part of the quantum mechanics too. So you will wait. You will hear about that. So don't worry. You will get the whole explanation about that. So I'm not going to explain everything, but there is a certain, of course, tiny problem with this perturbation theory, because here we have a lot of degeneracy in this story. So the degenerate perturbative theory. So the perturbation that we will here will be actually non-degenerate perturbative theory. But the funny thing is that here this is enough for us. So we don't need to go to a non-degenerate perturbative theory because that's what the wave function allows us to do. So it actually means that on non-perturbative, on non-diagonal terms, it's actually zero in this non-perturbative, in non-degenerate perturbation theory. So the perturbation theory here that we use is like a non-degenerate case. So okay, so saying that, so don't worry, you will hear everything. Now, what we do is we actually take the solution. So that's the idea of the perturbation theory. We take the wave functions from sorry. We take the wave function from the solution that we already did for H0. So that's the reason why we treated the problem, which was relatively simple, of the Schrödinger equation with Coulomb potential. Then we solved everything. So now we have a gross structure and the wave functions. So now this is sort of in addition to the Hamiltonian. So the true Hamiltonian that we are solving now is the H equal to H0 plus H fine structure, right? So and the idea is that this fine structure is much smaller than H0. So therefore, it does not actually affect for the first order, it does not affect the wave function of H0. So we only need to calculate the correction of the energy, so the expectation values of this correction. So the expectation values of correction is exactly the first order correction due to the perturbation theory. Okay, so now, having said that, we need to do that. So this is the correction of delta E, so the shift in the energy level, due to the presence of this relativistic correction of the kinetic energy, just equal to psi NLM. So essentially, we have, this is not enough, right? Because we know that there is a spin of the electron. So this is not enough now to describe the wave function. So we have to put also an additional quantum number, which is related to the spin. But here, we are still not dealing with the spin. So we can forget about that. So we can just solve this with the wave function that we know for the p to the 8th power divided by 8, m to the 3rd power c to the square, and the expectation value is the wave functions that we actually wrote a week ago. This is the procedure. Now, how to do that, right? So there is a simple way to do that. So the simple way is just to write it in a bit different form. So we can write this term as minus 1 over 2 mc squared, right? Multiplied by p squared divided by 2m squared, right? So this term can be written like that, and therefore we can actually say that this is nothing else than the kinetic energy squared of the original Hamiltonian. So if this is kinetic energy squared, then we can write that this is just the H0, the initial H0 minus the potential energy. So we can just continue that. So there's a minus sign here, of course. It should be taken. So we can continue this story and write it like that. So psi NLM. And this here, we write actually the H0 plus the potential energy, ZE squared divided by 4 pi epsilon 0 multiplied by R. That's the potential energy squared, and psi and n. So now we will quite fast understand why I insisted to write down many solutions for expectation values of the operator 1 over r, 1 over r squared, 1 over r third. We're going to use that quite immediately. So this is just because the Hamiltonian, right, the initial Hamiltonian is the kinetic energy minus the potential energy term. So then the potential energy term just goes into the H0 plus potential energy term and squared. Okay, so that's the story. Okay, now this square, right? We can just, instead of writing it as a square, we can write it like a multiplication H0 less ZE squared multiplied divided by 4 pi epsilon 0 r psi and n ln. Now we have to open that and see what terms are relevant and what are not, and what relevant, what not. So here we have H0 squared, right? H0 and H0 squared. So that's just E0 squared. So this is we already know. So we don't need to solve that again. So this gives us just so we know that there is some, okay, so I forgot. Don't let me forget that. This is the minus 1 over 2 times mc squared. This is this part, right? So it has to be kept. So now we have this steel story. But we can solve that quite immediately because we already did all the preparations. So H0 squared gives us En squared. That's the energy of the H0 Hamiltonian. So now there will be a term right here, which is multiplied by H0 multiplied by this term. So this term is actually applied on this wave function, right? So I can include in between the sum over all the wave function, right? Because this is 1, so it closes the H0 closes this term independently. So H0 give me En. This I know, the expectation value of En. And then this is the expectation value that we actually calculated. So therefore, there are 2 terms like that. One is the term like that. This from the left, this one, and this one, and this one, and this one. One on the left, one on the right. And okay, so and what I will get it 2 times multiplied by En. So En comes from the H0 multiplied by this part, ZE squared divided by 4 pi epsilon 0, expectation value of 1 over r to the n. And the additional term that I will have here will be coming from the multiplication of this guy. And this will give me 1 over r squared. ZE squared divided by 4 pi epsilon 0 squared multiplied by expectation value of 1 over r squared and n. So, and this is something that we already did last time, so we know the answer. So you have to go there and check the expectation values that we wrote, and then substituting them into this story. So essentially, we can summarize the correction. This is the order of the correction. So this order of correction can be actually summarized that delta E1 will be equal to minus En multiplied by Z alpha to the power of 2 divided by N squared. This is multiplied by 3/4 minus N divided by L plus 1/2. That's the correction due to the finite kinetic energy. First order correction due to the relativistic kinetic energy. So it's just some math to do. Here you get here the alpha, which includes the some everything about the E squared H bar C. That's enters into the alpha. So this is actually present here. So these are where these elements disappears. It goes into the alpha. Alpha goes into the squared. Alpha is the fine structure constant, right? Which has the relation between the E, C, and H bar into the unit. Yeah. Okay. So this is the first term. So the second term that we have to consider would be the spin orbit coupling. So the spin orbit coupling is a different story. So we have to walk a little bit more in order to understand that. Then it can be understood from also sort of a quasi-classical considerations. So the correction. So yeah, the story I can probably write it there because it will require some more space. Here comes the story, so with spin orbit coupling, here comes the story of the spin of the electron. So up to now we haven't seen that yet. So we have the following idea. So the following idea is like that. So what is the spin of the electron? The spin of the electron is a magnetic moment. So then the electron is rotated around the proton. The proton, we can see, instead of sitting on the proton, we can sit on the electron and see that the proton rotates around the electron. So the proton that rotates around the electron creates the current. Current creates the magnetic field. Magnetic field acts on the spin of the electron. That's the idea. Okay. So the orbital motion of the electron creates the interaction between the magnetic field, which is due to the proton, right? So if you change the coordinate system, the proton creates a magnetic field which acts on the magnetic moment of the electron. That's because the spin of the electron exists, right? So this is the spin orbit coupling. So in order to try to treat this story, we actually need to write the magnetic field as a derivative from the electrical field, right, due to the Lorentz transformation, right, in the rotating tray. So the magnetic field will be equal to minus 1 over c squared multiplied by v cross e. That's the electric field. So this is the magnetic field. The magnetic field that is felt by the electron in the sort of rotation of the proton when I sit on the electron and see the proton rotates around me. So this is the magnetic moment. So this is the magnetic field that is applied. So we have to calculate this magnetic field. So in order to calculate this magnetic field, we need to know what is the electric field, right? So the electric field is the inverse gradient of the electric potential, right? So the electric potential is the same as Coulomb potential that we know, is equal to ZE divided by 4 pi epsilon 0 multiplied by 1 over R, that's the potential. And therefore, the derivative of dE dr is equal to minus ZE divided by pi epsilon 0 4 multiplied by 1 over R squared. And now we get the electric field. So the electric field is equal to the gradient of this, of the B, derivative according to R. We get this ZE divided by 4 times pi epsilon 0 multiplied by 1 over R squared. That's the electric field. Yeah. And this electric field, we now, well, there is a direction of this electric field, right? The direction of this electric field is multiplied by R divided by R. So there gives me the R to the third power and the direction of the R. And now we are taking this electric field and substitute into this story in order to get the magnetic field. So the magnetic field then will be equal to minus 1 over c squared. And all these guys here is ZE divided by 4 pi epsilon 0. That's the constants here. Multiplied by 1 over R to the third power. And here I have R cross product with V. So I change the order. Therefore, there should be a correct sign then. Oh, sorry. Yeah, well, before I change. Yeah. So it goes like V cross R. So this is still the same order. Therefore, there's a minus sign here. And then if we just rotate this order and multiply by mass, so multiply by mass and divide by mass, in order to get the P. So P cross R, so R cross P gives us the angular momentum, L. That gives us the angular momentum of the story. So we multiply by M and divide by M and inverse the position of R and V. And we get that the magnetic field is actually equal to 1 over c squared multiplied by ZE divided by 4 times pi epsilon 0 multiplied by 1 over mr to the third power multiplied by multiplied by L. So the magnetic field is just related to the angular momentum. Now, this is the magnetic moment. This is the magnetic field. This magnetic field acts on the magnetic moment of the electron. This is the effect. So the magnetic moment of the electron, this is what we wrote before. The magnetic moment of the electron is equal to minus E divided by 2m multiplied by the gyromagnetic ratio, Gs, of the electron, gyromagnetic ratio multiplied by S divided by H bar, and this is multiplied by H bar, so you recognize here the Magneton Bohr, and here you have this S, the spin of the electron. So an additional story here in this effect is this, so the gyromagnetic ratio. This gyromagnetic ratio is an additional factor that enters into the story, which actually relate the gyroscopic motion to the magnetic motion, to the magnetic moment. So this gyromagnetic motion, moment, or gyromagnetic coefficient, is equal to 1 if we are talking about the angular momentum. So when we talked about angular momentum, the ratio between the angular momentum and the magnetic moment, this coefficient is equal to 1. But in our story of the electron, Gs is not equal to 1, Gs is equal to 2. So this is the result of the Dirac equations and the solution of the Dirac equations. So the solution of the Dirac equations requires the gyromagnetic ratio of the electron to be equal to 1, to be equal to 2. It's not equal to 1. So it's equal to 2 only for half an hour, right? Because then it's start to be suffering from other additional stuff. So it will be equal to 2 until the next week, because I'm a bit late today, I'm sorry. But we will get some corrections to this 2 due to some additional effects. We'll talk about that. Right? But this is 2, right? So right for now. At least the result of Dirac theory is 2.00000. That's the result of the Dirac theory. So nothing is added. So again, this is exactly integer 2. Okay, now, so now this spin orbit Hamiltonian that we are talking about should be equal to actually minus the magnetic moment multiplied by the electric magnetic field V. So magnetic moment, magnetic field V. That's equal to well, everything is here, right? So we have Z E squared divided by R4 times pi epsilon 0 C2 M2 R3. So from all this stuff, what is interesting is this 1 over R3. You already expect what is going on, so we'll have to find expectation value of the 1 over R3. But in addition to that, there's of course this multiplication of L and S, right? So here we have the spin of the electron, here we have the orbital motion. So this term comes from the interaction between the magnetic field and the magnetic moment of the electron. This gives the coupling. This is why it's called spin-orbit coupling. Right? The spin-orbit coupling is called due to the multiplication between the orbital motion and spin motion of the electron, the spin moment of the electron. This term gives us this additional energy density Hamiltonian. Well, this has to be multiplied by, so 2, I'm getting out of the story, so it's Gs divided by 2, which is equal to 1. Well, there is an additional story here. So it has to be minus 1/2 here. So this one is minus 1/2 here is due to another effect. So this is actually called Thomson rotation. So it's actually a classical effect. So everything here is essentially classical. So now we are, making some some classical considerations, though, you know, I could have been even, you know, treated other ways. So I would say that everything that we are seeing here can be derived from the Dirac Equation. So this comes from the Dirac Equation. That's it. But I'm not doing that. So I'm telling you sort of a story how it can be explained based on some classical intuition, right? So these are essentially all this story is just classical physics. And this classical physics also is to describe why we should take this term into account. If we know that there is a spin of the electron, so the spin electron comes from the Dirac equation, but all these considerations come from the just simple consideration of classical physics, and this additional term also can come from the classical physics, so you can actually find it in books on electrodynamics. This calls Thomson rotation. So it has to be taken into account due to the transformation of the coordinates when we go from in the rotating frame of the electron. So the rotating frame of the electron actually decreases this potential energy by a factor of 1/2, and it can be calculated from this story. So I'm not going to do that. So I'm just telling you that you can go to electrodynamics books and look for Thomson precession. Thomson and Thomas. I'm confused between the Thomas. Yeah, sorry. It's Thomas precession. The result is just due to the change of the coordinate system. So you go from the coordinate system which sits on the proton and the electron is rotating around, but you actually need to go to the electron and sits now in the rotating frame. So this rotating frame has this term. It is not just by chance that this term calls Thomas, because, you know, it was the guy was smart enough, you know, to understand that you have to correct that by a factor of 1/2. If you don't do that, then you get it too strong. This interaction is by a factor of 2 stronger than it actually was. So this was how it was calculated for the first time. So after you do all these calculations, you actually get to the solution, and you discover that you actually get it twice as strong as it should be. And it was Thomas who realized that, you know, due to the change of the coordinate system, you have to decrease this by a factor of 2. And this was since that called by Thomas precession term. I will continue next week, so we will finish this calculation next week. So we have to calculate still the spin orbit rotation and the Darwin term. We will do that next week. I'm a bit slow today, so I'm sorry. Probably because of hot weather. So next week it will be better. We will go faster. So remember that there is a first problem set on the. Did you see that? Have you put your attention on the fact that there is a problem set that you have to return in a week from now? Well, there is actually, until the Sunday of the next week. So you have the time until the next Sunday. So remember to bring it to us, to me, or to the tutor. So to who is still not here, but he will be with you. But at least he will start to check your problem sets. So, and within a week, I will release the second problem set. So, and there will be no, prolongations. Okay. Okay. So, see you next week.